Okay, we're going to work on page C. Okay, your 60 seconds. Oh. Okay, awesome. Come up here. Just want to remind you, holes are considered to be removable discontinuities. Jumps are not. They're non-removable. Okay? So we're working on page C, and we're going to work on finding out limits. First one, number 1, limit as x approaches power of 2 of x over the sine of x. Now, if you just type this into your Inspire calculator, there's a limit command built into the calculus menu on the Inspire calculator. It lets you put a plus or minus there from right to left. It's got a little template for that thing. It just gets it right every time. Be careful whether you're in degree or radian mode. You want to be in radian mode in calculus test. Want to consider radians. The answers won't be the same. Okay? But it just does it. If you graph this function, not an easy function to graph, but if you use your calculator graph and looked at the graph, then it would become a problem just like we just did. Remember we did 3 pages of those where you just look at the graph, which is something you must be able to do, look at the graph and see the limit correctly. But in this case, it's a little bit harder, but we're going to take advantage of the idea of continuity. If it's continuous, then the value there is what the limit is. And this does have some issues with continuity. Whenever the sine of x is 0, it would not be continuous. So when x is 0, when x is pi, when x is 2 pi, we have no problem with pi over 2. So really, we just plug in. We get pi over 2 over the sine of pi over 2, which is pi over 2 over 1, pi over 2. That's going to be our answer. So when you're doing limits, your first thought should be just plug it in. Because if the curve was continuous there, and you plug it in and get a value, then that's your answer for your limit. Okay? Now, we're going to learn that the limit is x approaches 0 of x over sine of x, which is, it's not always, it's not normally this, but it's the limit is x approaches 0, sine of x over x is 1. We're going to learn that. And so a lot of students, they get this. It's one of the things I make you memorize on the stimulus reaction sheet. I just realized I forgot to hand something out to you. So a lot of people answer 1 on that, but they shouldn't. Okay? We're not there yet. It's the end of the chapter to do that. Number 2 is like this. So we're going to skip for now. There's no way I can expect you to do number 2 right now. Number 3. Definitely can expect you to do. The limit is x approaches 9 of 3 minus the square root of x over x minus 9. We'll use the same idea. We'll just plug in. Just plug in. If I plug in 9, I get 3 minus the square root of 9. It's 3 minus 3. 9 minus 9. We get 0 over 0. Whenever you get 0 over 0, the answer could be anything. It could be positive thing, it could be negative thing, it could be 1/2, it could be negative 1/3. It's amazing. 0 over 0, because we're approaching 0 over 0. Someone might say it's 1, someone might say it's 0. 0 divided by a number is 0. Someone might say you're dividing by 0, so you get infinity. The fact is, we're approaching 0 over 0. And so we're not sure what's happening. And so we have to do some algebraic manipulations. And in this case, there's 2 good choices. I'm going to do it both ways. One way, and I'll take suggestions. Anyone have a suggestion? Mike?
You could factor out the negative sign from the denominator and it's faster.
Why do you have to factor a negative sign out to factor it, though? I mean, you could do that. And it's you sort of at the end going to have that negative deal with one or the other. But to factor, what do you factor? The top or the bottom?
The bottom.
What's it become?
It becomes x, the square root of x minus 3 times the quantity.
Square root of x minus 3, square root of x plus 3. Okay? So I understand what you did. You pulled a negative out and see it the other way. But I think this is a recognition that this is difference of squares. This is real high-end difference of squares because there's no square there. You have to recognize it's the square root of x squared minus 3 squared. Square root of x plus 3, square root of x minus 3. And if we do that, what happens to the square root of x minus 3 and 3 minus the square root of x?
Yeah.
They cancel and get you -1. They're opposites. You have to know that a minus b over b minus a is -1 without hesitation. It's -1. And so our problem is the same as, so we don't care about what's happening at 9. You understand? This problem doesn't care what's happening at 9. It cares when we approach 9. If we're close to 9, it matters. And when we don't have 9 itself, we actually have the same thing as -1 over the square root of x plus 3. And now we plug in the 9 and we get -1, 6. The answer is -1, 6. The other method is to multiply by the conjugate. 3 plus root x top, 3 plus root x bottom. So we took the 3 minus root x, we multiplied by 3 plus root x top and bottom. The top then can be expanded into 9 minus x. And it's totally the same. That gets us to -1. So a minus b over b minus a gets me -1. So now we plug in the 9. We have -1 over 3 plus square root of 9. Same answer, of course. Two really different methods there. Algebraic, no calculator needed. Pretty high end. I'm hoping you catch on to that. Okay? Mark, can you read number 4 for me?
The limit as x approaches -infinity of x plus 2x squared minus 3x cubed all over 3 plus x minus x squared plus x cubed.
I'm hoping many of you from pre-cal, certainly pre-cal honors, should know the answer instantaneously. What's the answer instantaneously? -3. How did you get that?
You take the highest x thing.
X cubed, highest degree, top and bottom.
And then the number in front of it is the answer.
Coefficient -3, coefficient 1, we take the ratio of coefficients. Even in Algebra 2 honors, we talked about this. We talked about horizontal asymptotes. Okay? Well, the horizontal asymptote is the y value that we're approaching as x goes to -infinity. So we take the limit to get the horizontal asymptote. And it's going to be the ratio of the coefficients, the highest degree terms, if they're equal. What if the top is bigger than the bottom? No limit. What if the bottom is bigger? 0. You divide by a huge amount, you get 0. What really could be done is look at the bottom. The highest degree is 3. So multiply top and bottom by 1 over x cubed. This is what's really going on behind the scenes. Now, I'm not saying that you have to do this work. I'm really expecting that you knew the answer is -3. You mark a -3, you move on. But if you're having trouble about why that is, I'm going to have to multiply top and bottom by 1 over x cubed, right? I multiplied by a reasonably clever expression for 1. I consider it clever, but when this goes in, we have 1 over x squared plus 2 over x minus 3 over 3 over x cubed plus 1 over x squared plus -1 over x plus 1. Now, what happens to this number as x gets huge? It goes to 0. What about this one? It goes to 0, and this, and this, and this. They all go to 0, and so what are we left with? -3 over 1. That's why it works. That's why it works. Okay? So that's the work you need to do if you had to convince someone. But when I give it to you on the test, you get one on the test. You should say, hey, I'm going to infinity or -infinity. Let's look at the degree of top and bottom. They're the same. Take the ratio of the coefficients. Done. That only works for rational functions. Polynomial on top, polynomial on bottom. Polynomials are smooth and continuous. Very nice to work with. Okay. 5. Harrington 5.
The limit as x approaches 0 from the left of absolute value of x over x.
Now this is one that I'm hoping you just remember the graph. You see absolute value of x over x. I'm hoping that you remember, because I tried to teach this to you in Algebra 2 as a preview of this. And I know you don't remember everything, but it was this thing. It goes like that. For positive numbers, these are the same, and then you divide out, you get 1. But for negative numbers, this is negative x over x, and we get negative 1. So what's the answer to that, Harrington?
Doesn't.
What's the limit as x approaches 0 from the left?
Negative.
Negative 1. You were doing, Harrington was doing the limit as x approaches 0. It doesn't exist. If there had been a plus, she should have answered 1. But since it was a minus from the left, the correct answer is negative 1. Now, you could do the graph and figure it out, or you can start thinking. You can think about it this way. Since x is less than 0, negative, the absolute value of x is the opposite of x. So we have the limit as x approaches 0 from the left of negative x over x, which is the limit of negative 1. And negative 1 is always negative 1 is always negative 1. So what's negative 1 going to? Is x goes to 0 from the left. Negative 1. That would be another algebraic way to do it. It's supposed to be so hard. Okay, let's get a couple more done. That was 5, 6, please, Mikey.
Consider f of x equals
Piecewise defined. Okay,
2x plus 2 if x is less than 3.
and this was cut off. It should say x is greater than or equal to 3 there. Okay, so they want the limit as x approaches 3 of f of x. And you got to be careful on piecewise defined. I think it's on your semester X's somewhere. When piecewise defined, watch out for the boundary values. Right here at 3. What's going on from the left, Mikey? What's the limit as x approaches 3 from the left of f of x? Aren't we riding this curve?
Yes.
So what's it going to be when x approaches 3?
8.
It's going to be 8. And what's the limit as x approaches 3 from the right of f of x? X is bigger than 3. We're from the right, so we're bigger than 3, so we're riding this curve. What's it going to be approaching?
8.
So what's the overall answer?
8.
8. We got the same thing. You're going to have to do both sides. You have to do both sides and make sure they're the same. If they're different, we say does not exist. Does not exist. If they're the same, we say whatever number we got. Charlie?
So for piecewise defined, you just plug them in to find that?
They were asking for what's going on at 3. As x approaches 3. 3 was the key thing. This is a nice continuous function until we get to 3. This is nice and continuous until we get to 3. You could have piecewise defined with pieces like that in the middle, and we'd have to do more work. Okay, but your first thought is to plug it in. Since it's piecewise defined, we had to plug it into both halves. So I think that answers your question. And, okay, 7 is the answer, and it's what's the answer going to be? It's going to be 0. Okay, we sort of went over that before. You can multiply by 1 over x cubed top and bottom. The top will become 0, the bottom will become like 7. So 0 over 7 is the top, the bottom will become 1. Number 8. Yeah, one more done here. We have x squared minus 5x over 25 minus x squared, and we're approaching 5. The first thought is plug it in. You get 25 minus 25 is 0, 25 minus 25 is 0. Whenever you get 0 over 0, the answer could be anything. It could be anything. So we need to do some algebraic manipulation. I'll show you another way later in the year that you really like once you know some calculus. But I factor this, 5 minus x, 5 plus x, and standard. Do you recognize anything there?
The x minus 5 and 5 minus x cancel equal -1.
So we actually have the same problem. We're not at 5. We're not at 5, and we're not. We're approaching 5. We're not at 5. We're approaching 5. This is the exact same problem as negative x over 5 plus x. Plug 5 into that, and what do we get? Negative 1/2. Negative 5/10. Negative 1/2. Okay? That's all we're going to do. You can stop that. I got to get to